Hi everyone, what I want to do now is talk about some applications of the Hahn-Banach theorem. And in particular, I want to do some very concrete applications to duality of LP spaces. I'll talk about duality for the Bergman space, and actually duality of Sobolev spaces, at least on 0 to 1, will be a homework. Yeah, I really want to kind of, with this lecture, try to emphasize just how powerful and useful in very concrete situations the Hahn-Banach theorem is. Okay, so, right, so applications. And in another video, I will talk about some more theoretical applications of the Hahn-Banach theorem. I'll talk about reflexive Banach spaces, double duals, and things like that. And then we'll just dive into the closed graph theorem and open mapping theorem. I'll try not to spend too much time on those. Anyway. Okay, so we need the following lemma before I even remotely talk about applications of the Hahn-Banach theorem. And this is a lemma that's a consequence of the Hahn-Banach theorem. Basically, most applications of the Hahn-Banach theorem really hinge upon this fairly easy lemma. So let's say X is a normed vector space, does not need to be complete. Let's assume it's not 0. It's not the 0 vector space. All right, so let's say I'm given x0 and big X not equal to 0. So I claim there is a bounded linear functional on big X where the norm of this bounded linear functional remember, F could be reals or the complex numbers, and in practice, it's really, it could be either. If you're doing functional analysis, it's usually the complex numbers. Depending on your situation, if you're doing, PDE theory, it's oftentimes the real numbers. If you're doing like, D-bar equation stuff, PDEs for several complex variables. Obviously, you want to deal with complex numbers, dealing with complex variable theory. So yeah, we claim that this is 1. And last but not least, I plug this in here. Sorry, phi tilde. Maybe I'll get rid of the tildes here, not very important. This here is going to be the norm of x0. Okay. And the proof is very straightforward. Let's first cook up a useful vector subspace, M, and that's just going to be the span of x0, which is just obviously all alpha x0, such that alpha is real or complex, depending on what field we're dealing with. And let's define kind of the obvious bounded linear functional on M. Let's say phi 0 on M is given by the following. Well, everything in M is given by alpha x0. So So this is just going to spit out alpha, the norm of x0. So on M, you can check very easily this is linear. It's linear just because, well, everything in M is just a scalar times x0. So there's no variation in the x0. It's just the scalars here. So this is going to be pretty obviously norm 1. And you can just see this very easily. Again, everything in M is given by alpha x0. So yeah, so let's look at this here. Assume alpha is not 0. Well, this here is obviously 1. This norm here is, well, this is just going to be absolute value of alpha, norm of x0. This is absolute value of alpha, norm of x0. So this is 1. That obviously means that from at least M to F, this is 1. So yeah, what we do is just take a Hahn-Banach extension. Let phi be a Hahn-Banach extension of phi 0 to all of x. Okay, so that means because Hahn-Banach extension by definition is norm preserving, that means this is going to be, well, 1. Okay, so that takes care of kind of half of what I wanted. That's this half here. And let's check that we get x0. Well, this is pretty trivial. So this here, 5x0, is given by, well, 1x0. And obviously, this is an M. So phi is phi 0 on M. Phi extends phi 0 from M to all of x. Right? So this is going to be given by, well, 1, this is my alpha, times the norm of x0. That's obviously norm of x0. And that's the other piece that I wanted. That's the second half. Okay. So an innocent looking but very powerful result. So let's see why this is so useful. Well, basically a fairly straightforward corollary of this is the following, which definitely I probably should call it its own theorem because it's extremely important. So it says that if x0 is in big X, then the norm of x0 is given by the supremum of, we'll dump in x0 over, dump in x0 into a bounded linear functional of norm 1. So up a bit. Right, so it's a supremum of all these non-negative numbers here. Okay. Sorry about that. All right, so let's Yeah, so one direction is fairly trivial. So let me call this, well, okay, let's not call anything anything. Yeah, one direction is pretty trivial. So if I have a bounded linear functional with norm 1, well, then this is obviously going to be less than or equal to, well, the norm of x0. Sorry, this equals 1, then this is going to be, yeah, this equals 1 here, so it's the norm of x0. That implies, well, this is an upper bound for this whole set here I'm circling in green. Sup is the least upper bound. So as the least upper bound, the sup of this whole thing here is less than or equal to the norm of x0. So we just need to show the other direction. And that's where this lemma comes into play. So I should just mention, you know, in a research paper or even some more advanced textbooks, they would probably just say, well, the author would just say, well, by the Hahn-Banach theorem, the norm of x0 is given by the supremum. And it's not really inaccurate. It's really by this lemma here that basically is a corollary of the Hahn-Banach theorem. But anyway. All right, so we need to show the other direction. So to show that x0 is less than equal to the supremum, well, by the lemma I just proved, pick phi in x star, the dual space, norm equal 1, where the norm of x0 is given by phi of x0. Well, obviously then this means that this is not negative, so it is equal to its absolute value. So let me just put, well, whatever. So this is one individual, one single phi with norm 1 in the dual space. So that one single individual one, particularly phi of x0, for this one particular phi satisfying these conditions here, is certainly less than or equal to the sup of all such numbers. So that proves it. Any one individual is less than or equal to the sup. Sup is an upper bound. So that implies its x0 norm is equal to the sup. Okay, right, so really it's a maximum, but we basically proved that it's a maximum, and the maximum is achieved somewhere by the Hahn-Banach theorem. But still, most people just use the sup, particularly because you know, you really can't construct, generally speaking, you can't actually construct your bounded linear functional where the maximum is achieved, where the actual norm of x0 is achieved, because, well, Hahn-Banach theorem in general rests upon Zorn's lemma, and it's not constructive. You just know that it exists. So you really don't care that it's a maximum. You don't really care whether or not you can construct it. You usually can't. You just care that it exists So anyway. Okay, so a fairly obvious corollary, so maybe I'll call this a theorem. It's worthy of being called a theorem, so I'll call it a theorem. So a pretty obvious corollary, which is nevertheless quite useful and implicitly used all the time, particularly if you want to get concrete bounds on bounded linear operators for explicit norm vector spaces. So if I have two norm vector spaces, x and y, and T is a bounded linear operator from x to y, then the norm of T is given by the following quantity. And really this corollary says it's very useful to know what bounded linear functionals on a norm vector space looks like. Okay, so we're going to look at the soup of all this, where phi is bounded linear functional on y. Phi has norm 1. And so does x. And to be clear, this is the norm of x on big X. Yeah, the proof, there's really not a hell of a lot to it. Just definition and the previous theorem. Right? So, right, so the norm of T, so from X to Y, so let me just not write norms. It's implicit what norm is attached to what object. So this here, by definition, is the soup of Tx, norm of Tx. Don't have room here. Well, the norm of Tx is an element in Y. Okay. We're assuming this is bounded. So Tx is in Y, so this here by the previous theorem is going to be, oops, sorry about that. Well, it's just its iterated supremum. So the norm of Tx for any x is given by the following here. Well, you can always write an iterated supremum basically as one single supremum. So I don't feel like rewriting this. So this is going to be equal to star. So yeah, basic analysis. If you have any doubts about that, just check. Prove it yourself. It's pretty straightforward. Okay. Right. So yeah. So the obvious point is that if you want to get a good concrete bound for a bounded linear operator, then it's very helpful often to know what the dual space looks like, particularly when x equals y. Knowing what the dual space of x looks like is extremely useful. So what I want to do now, spend some time on, is some very concrete examples of dual spaces. Right, so let me look at a very simple example first. and that is the dual space of little LP. So this example will kind of sort of tell you kind of how to figure out and prove in particular that the dual space of a regular big LP is LP prime if P is between 1 and infinity, including 1, and P prime is the conjugate exponent. The proof is a little more complicated than for little LP, but sort of the same. All right, so if P is between 1 and infinity, then the dual of little LP is little LP prime. Okay. So, right, so what do I mean even by this? Well, I mean that every bounded linear functional on LP, little LP, is given by phi y, where y is an element of little LP prime, and phi y is given by basically x inner product y. I mean, we're not dealing with a Hilbert space, so technically there are no inner products, but it's basically x inner product y. Okay. So one kind of thing I want to emphasize and make clear, this is clearly linear, and by just the discrete Holder's inequality, this is pretty obviously less than or equal to, whoops, sorry about that. Just smash in absolute values, modulus, whatever. This is going to be less than or equal to the LP norm of x, LP prime norm of y. So that implies that in particular, this is linear or bounded, and this here is less than or equal to the LP prime norm of y. So yeah, so I'll prove the converse. I'll prove the converse in a moment, but I just want to clarify, particularly by this note, that this actually itself does define a bounded linear functional, and we're claiming that every bounded linear functional on LP is given by phi y for some y. Okay, and we'll prove that, in fact, this norm equals the little LP prime norm of y. Okay, so what is the proof? So the proof is the following. And I'll give, yeah, we'll talk about, I'll talk about the dual of L infinity in a moment. So I'll leave that aside for the time being. Won't talk too much about that, but I'll talk a little bit about that. All right, so, well, how do we do this? Well, pick something in the dual space of LP. So let's say phi is in the dual space of LP. And as customary, I'm not writing the natural numbers, just a pain in the ass to keep writing. Okay, so So let's say X is in little l p. So you can write X basically almost like an orthonormal expansion where the ENs are kind of your standard orthonormal basis for little L2. I mean, the same thing works for any sequence, really. So just make sure we're all on the same page. En is just going to be all zeros. Except at the nth spot. Okay, so yeah, I claim that this is actually in little LP, that this sum converges in little LP. Okay, so in particular, this here, so I should mention, of course, En is itself obviously in little LP. I mean, the norm is 1, pretty trivial. There's only one non-zero spot, and that's the nth spot. Everything else is 0, and the nth spot is 1. So yeah, pretty trivially, well, this is going to be, yeah, so this here is just going to be simply, if there's any doubt at all, this sequence here is just going to be x1, whoops, sorry about that. There we go, right, like this, x1, x2. Well, after it, everything is 0. So, yeah, you get the point. Everything after the nth spot is 0. So yeah, pretty trivially, this is going to be equal to n equals n plus 1 to infinity of xn to the p, modulus that. And because x is in little LP, this, as n goes to infinity, converges to 0. Okay, so the point here is, in little LP, we have the following convergence, which is not a terribly deep observation. I don't want to make it seem like it is. It's pretty damn trivial. But it's extremely useful because what I can do now is, because this is a continuous linear functional, bounded is the same thing as continuous for linear functionals. So phi of x is going to be phi of this infinite sum here. By continuity, this is going to be the sum. Well, xn is just a complex number. En is my element in little LP. So this is going to be xn phi of En. Okay. So right here. Right, so this here is certainly in C, okay? So now it's pretty obvious what you want, what Y has to be, okay? So if we define Yn to be the complex conjugate of this, then obviously we have this as true. So the only thing to do now is prove that, well, first, yeah, let's prove that y is in little lp prime. And basically at the same time, let's finish up the other half of this here. You know, basically we did half of it already. Half of the norm equality is this here. So now we have to do the other half. And the proof strategy here, you might have seen it for big LP. It's certainly in Royden's book, Royden, Fitzpatrick, Real Analysis. You have to be a little more careful here. In particular, we do not know that y is in little lp. So we have to be a little careful here. Not that careful, but a little careful. So just to maybe try to make this a little clearer. So if y equals, well, y1, y2, so then we have phi x is going to be phi y of x. Again, phi y of x defined in this way. Okay, so what we do, and this is really an important trick to remember, I would say certainly in harmonic analysis, anytime you're trying to prove something is bounded, particularly an operator is bounded, this is something to keep in the back of your mind. You know, and that is you kind of truncate your operator or truncate your element in your norm vector space to force it to be bounded or force it to have a nice norm that depends on your truncation, but then you prove that in fact it did not depend on your truncation. So what on earth do I mean? So let's say, right, so let's define for a big N, I'll explain what big N is. Well, big N is just a natural number. So define Yn in little lp prime by the natural truncation of y, big Y. In particular, it's just Yn if n is an integer less than or equal to big N and otherwise 0. So there's absolutely no ambiguity that Yn for each fixed n, big N is in little lp. Any finite sum is finite. There's no ambiguity at all. Okay. Okay, so we're going to do a nice trick. So what I want to do is define something. So yeah, let's define something I want to plug into basically my bounded linear functional to extract some useful information. Okay. Or in other words, as we like to say in harmonic analysis, we're applying a testing function. We're testing my bounded linear functional on some x to get some useful information. And this is admittedly fairly clever, what that's going to be. But Okay, so let's say this here is also, well, 0, basically if, I'll write it like this. Then it's bigger than n. And let's say it's going to be, so first, let's assume y is not 0. If y is 0, then basically there's nothing to do. I mean, that just means your original bounded linear functional is a 0 bounded linear functional, and everything is 0, so it's really nothing to do. So let's assume that loss of generality y is not 0 for large enough big N. This means that for large enough big N, that at least one of these numbers here, y and big N, one of the components is not 0. So in particular, for large enough big N, the norm of yn is not 0. So I'm fine writing this here. Okay, P prime. 1 minus P prime. And so this is going to be yn n over the absolute value of yn yn absolute value of n to the P prime minus 1. Right. Yeah, so let's actually consider the case. First, let's look at the case P is between 1 and infinity. All right, yeah, so here P prime is unambiguously defined as, well, just a dual exponent. 1 minus 1 over P, or explicitly, P prime is just P over P minus 1. Okay, so if we take xn and plug it into phi of y, then what are we going to get? We're going to simply get the following sum here. Well, xn is 0 if n is bigger than n. So we're going to go from little n equals 1 to n. So it's going to be xn n, and then it's going to be yn. All right, so what is this? Sorry for the slant. Let me see if I can fix this. That's much better. Sorry about that. Okay, so this is going to be the norm of yn to the, by definition, 1 minus P prime, yn to the n over absolute value of yn to the n. So it's a bit of a mess, but, and implicitly, of course, xn, the big N, is going to be 0 when yn is 0. So, so I'm not going to write that, but okay, so it's yn to the P prime minus 1. Well, really, so for n less than or equal to big N, it's just yn. So we're justified in getting rid of the big N's. And here it's just yn complex conjugate. So this is just going to be, and this is the little LP prime norm. So you can see what this is going to be. LP prime, 1 minus P prime. Well, this is just going to be at modulus yn squared. That cancels this. So it's modulus yn. Well, that makes it yn to the P prime. That's all that's left here. So it's yn P prime. And this is going to be, well, again, yn is yn big N when restricted to little n between 1 to n. So this is going to be y big N to the 1 minus P prime, little LP prime, y big N, little LP prime, whoops, sorry about that. Running out of space here, so I got a little sloppy there. Little LP prime to the P prime. So these cancel out, the minus P prime and the P prime. So we get YNNL P prime. So what's the punchline here? The punchline here is that the norm of yn big N, or rather, sorry. Yeah, sorry about that. Should not have an N here. My apologies. And this is little L P prime. It's a little messy, but so, right. So here's the punchline. This we computed to be, well, it's, you know, if this is going to be, this says all this here that this is non-negative, so it's equal to its absolute value. So really no harm in throwing absolute values in. But whatever. So this says that this here is going to be absolute value of phi y of x n. Well, this is equal to phi y is equal to my original bounded linear functional. So this is less than or equal to, well, just the norm of phi from LP F times the norm of xn LP prime. And you can check that the norm, basically by design, the norm of xn is just going to be 1. The little LP prime norm of xn is just going to, sorry, it's LP, not LP prime. Doesn't make sense. That would be LP anyway, LP prime anyway, it's LP. But you can check by the way we defined xn in this fairly clever way that this is going to have norm 1. So it's going to be equal to this is going to be equal to the norm of phi. Okay. So what you could do now is just basically just let big N go to infinity. Okay. So what is this? What is this? This is literally going to be n equals 1 to big N of yn to the p prime 1 over p prime. This is what the LP prime norm of yn is. This is less than or equal to the norm of phi from LP. That's just what we got right here, LP to F. Okay. Now we can let n go. Let big N go to infinity. Okay. So right. This says that, in fact, y is in little LP prime. Beforehand, we didn't know that. We cannot define xn, this xn big N, without knowing that we have something that's in little LP prime. I mean, you can't really divide by, it just doesn't really make sense. You know, you would be dividing by really just dividing by infinity, which would set it to be 0 everywhere, which doesn't make sense, really. So it's just the proof falls apart unless you're dealing with something you know beforehand is in little LP prime, and that is y big N. You know y big N is in little LP prime. And this also shows that the LP norm, LP prime norm of y is less than or equal to the norm of phi. And that finishes the proof since we proved the other direction already. Okay, so I just want to state what is true for big LP. Actually, I should let me just really quickly do the case p equals 1. So p equals 1, you basically do almost the same thing. It's really not that much different. You set xn big N to be, well, still 0 if y and big N is 0, and otherwise you just much more simply set to be yn over modulus y and n. Otherwise, if this is not 0, and the rest is the same. Again, you assume that at least one of the y's is not 0, one of theyn's. So for large enough n, this here is not the 0 element. So then the L infinity norm is obviously 1 by this definition here. And then you plug, you know, basically the rest is the same. You can check yourself. That really the rest is exactly the same. So it's a little easier when p equals 1. Okay, so let's state what's true for big LP. It's a little harder to prove. You need more advanced real analysis. If you want, again, the proof is in Royden. So it's as good as any reference for this result. So let's say S is a subset of Rn. really this proof works for any measure space whatsoever, but just stick to Euclidean space. So every bounded linear functional and again, let's say 1 is less than or equal to p is less than infinity. So every bounded linear functional on LP is given by well, basically the same thing, phi g for some g and LP prime. And what is phi g of f? It's just, well, f inner product g, essentially. Yeah, G is an L, P prime of S. And furthermore, basically the same proof that we employed. It's a little easier because here you're assuming G is an LP prime. Yeah, so this here, this norm here from L, P of S to C is going to be equal to the LP prime norm of S. Okay, so I want to do one last thing, which I think is quite interesting. So actually, yeah, I do want to do 2 more things. So I don't know if I'll collect this. So another, well, all right. So let me make a note here. Well, what about L infinity, the dual space of L infinity, both little L infinity or big L and little L infinity? So one thing we know, really absolutely trivially, and you could say the same thing for little L infinity, we know that big, let's say S is any subset of Rn. Again, what I'm writing really works for any measure space whatsoever. We certainly know that L1 of S is a subset of the dual space. Again, via the same thing. This is given by S, f of x, g bar of x, for G in L1 S. So we're saying each G in this sense, as we've been doing throughout this lecture, defines an element in a dual space. And that's absolutely trivial. Just smash in absolute values. This is less than or equal to the L1 norm of F times the L infinity norm of G. So this is certainly in the dual space. Okay, so let's state a little proposition, which itself is a really beautiful application of the Hahn-Banach theorem. So just to keep things simple, I'll stick to the real line. In fact, we just proved L1 is the subset of L infinity, the dual of L infinity, but the dual of L infinity is larger The dual of L infinity is a rather complicated object. It's usually in a course like this, you don't talk about really much, or rather you don't try and explicitly define the dual space. It's just so large that it's really complicated. In a more advanced course on Banach space theory, you would talk about the dual space of L infinity. But so let's at least prove the following proposition, that L1 is strictly smaller than the dual space of L infinity. And basically, what's going on is, well, here's what's going on. So typical of Hahn-Banach applications, let's pick a convenient subspace. And for us, that's all continuous functions on the real line that are also bounded, all bounded continuous functions. So C of R means just continuous functions on R. Let's define a very useful bounded linear functional on M, and that's just a Dirac delta functional. And that is just, well, f of 0. So this really here is popping open the kind of door to the theory of distributions, which is extremely useful in certain areas of PDE theory, particularly in mathematical physics, quantum mechanics. Professor Alexandrova is probably the department expert on the theory of distributions. Yeah, so I would talk to her if you're kind of curious about that. Okay, yeah, so yeah, obviously this has L infinity norm, this has, sorry, phi 0 has norm 1, because this here well, this is less than or equal to the norm of L infinity. Take something kind of trivial. Let's say F is identically 1. So that. Then obviously phi phi of f, phi 0 of f is 1, is L infinity. So that pretty clearly, basically from what we've done before, by definition, tells us that, and if you have any doubts, just check it yourself, that this has norm, this has norm 1. Well, actually, we don't really actually care that it has norm 1, but all we care about is that it's bounded. So let's get rid of this here. Sorry about that. Yeah, so phi 0 is certainly in the dual space of M. Okay. So let's say phi tilde be a Hahn-Banach extension of phi 0 to L infinity. So let's assume that this Dirac delta function, or rather, let's assume the Hahn-Banach extension of this Dirac delta functional is delta function, functional, whatever, is given by a function. So let's suppose that phi tilde is of the form phi g for g in L1. So let's define a convenient function to plug in. And this is actually a quite simple function. I'll draw a graph in a second. 1 minus n, n is an actual number, 1 minus n absolute value of x for x between minus 1 over n and 1 over n. Let's say 0 otherwise. So the function here is just, well, basically it's just like a roof, kind of. So here's 1 over n minus 1 over n. Yeah, so it's 0 here and you know, has slope obviously. Well, here it has slope n, here it has slope minus n. Right. So obviously this is an L infinity. This has L infinity norm, you know, trivially equal to 1. But in particular, it's an L infinity. Okay, so what does this tell me? Obviously, plug in 0, you get 1, no matter what n is. This is obviously continuous. It's just you're piecing together a continuous function. It's piecewise continuous. I mean, you're piecing together continuous functions that coincide at these endpoints, 1 over n and minus 1 over n. So each fn is continuous. So it's particularly in big M. So this is going to be equal to the following. So this is going to be the following limits. Fn of 0 is phi 0 of fn. Okay. Well, this is going to be given by the following. It's phi. Okay. Well, we're assuming that, well, it's phi tilde, because it's an extension of phi 0. So this is going to be the limit phi g of fn. So this is going to be given by this, yeah, it's going to be given by this right here. Fn of x, g bar of x. So by dominated convergence theorem, well, Fn fairly obviously converges to 0 almost everywhere. So this is going to just converge to, G is an L1. So, I mean, your dominator is just absolute value of G. So all you need to do is, yeah, so all you do is just say that just use dominated convergence theorem. And this is going to be, well, 0, integrate, you know, this it's just 0. Right? So, yeah, this is impossible. This says that 1 equals 0. Okay, so what does this basically say? Well, we've basically proved that we have this bounded linear functional on L infinity. where phi is not phi g for any g in L1. And really, G is not going to be in any LP. That's pretty trivial because you can use dominant convergence theorem if G is in any LP whatsoever, because, you know, Fn is 0 away from -1 to 1. Okay, so yeah, and you again, typical of Hahn-Banach theorem, you don't know what this phi tilde is. You do not know what this bounded linear functional is that is not given by an L1 function for any L1 function. You just know by Hahn-Banach theorem that it must exist. All right, so I want to do one last, so I'll explore more of this in the homework. Same thing is true for little L1. But we'll explore this in the homework. So I do want to make one final application of everything we're doing, particularly just Hahn-Banach theorem directly, to the Bergman space. A somewhat similar argument applies to the Sobolev space. You know, because in particular, the Sobolev space you can basically think of as kind of like a subset of, you know, sort of a subset of LP, really a subset of little let's say Cn valued LP. You know, your Cn vector function is kind of like let's say f prime, and all derivatives. Well, we only dealt with order 1 Sobolev space, so it's really kind of like you know, C2 valued LP. You know, you have f and its weak derivative. But I'll talk more about that if that's not clear in the homework. Yeah, in the homework we'll explore the dual space of the Sobolev space. All right, so let's write a fact, and this fact is a little messy to prove, so I won't do it. Actually, what you do, you prove it by using a LP version of the Schur test. You can just Google that for an easy LP version of the Schur test. So let's define this, you know, Bergman projection-like operator as follows. It basically is a Bergman projection, Bergman space projection from L2 to A2, but with absolute values smashed into it. So if we have these two, and let's just, instead of thinking of P, the Bergman space projection from L2 to A2, instead of thinking it as a projection, an orthogonal projection, but thinking of it as an integral operator, let's just say P f of z is literally this integral operator, sorry, W. Then a few things are true. Yeah, what's messy, I mean, the Schur test for LP is very straightforward. The proof is basically the same proof that you're doing for homework. Instead of using Cauchy-Schwarz, you use Holder's inequality. But finding the correct testing function is definitely messy. You have to do, it's messy. It's a bit involved, but basic idea of doing this is just use the Schur test. Okay, so 2. Well, certainly if P tilde is bounded, then fairly trivially prove that this is bounded from LP to LP. But we don't want just that. We want to actually, well, we want that actually PF, when F is an LP, is a holomorphic function. So it actually takes LP to AP. Sorry, P is between 1 and infinity. Actually, P can be 1. I believe. No, I don't think P can be 1. Anyway. Yeah, so this is bounded. And 3, we know this is, so we certainly know 2 is true for P equals 2 because it is the orthogonal projection from L2 to A2. And we know when P equals 2, P restricted to A2 is the identity because it's an orthogonal projection from L2 to A2. And that's true in this setting too. This is just the identity. All right, so assuming this, we can relatively painlessly, again, thanks to the Hahn-Banach theorem, prove that if P is between 1 and infinity, then the dual space of AP is going to be AP prime. So the dual of A1 is a little bit complicated. Well, it's called the little block space, if I remember correctly. I haven't looked at the little block space in years, many years. I think it's a little block space, if that means anything. If not, that's fine. Yeah, so there's no complex analysis here, which is nice. That's what I want to emphasize with this proof. There's virtually no complex analysis. So actually, what I want to do, so it's a little different than LP duality because so furthermore, if we have G is an LP prime, and maybe to make clear first, so it should be clear what I mean by this, but if not, so I mean that if we have some bounded linear functional, I'm sick of writing the disk, so. There exists G in LP prime, where for any F in AP, this is going to be given by just integration with respect to G bar, it's phi G of F, and this is for any F in AP. Furthermore, so if you think about it, so maybe I shouldn't say think about it because I didn't really go through the LP proof of finding the the norm of this bounded linear functional phi of G. I just said it's kind of similar to what we did for little LP. Basically, you can imagine now if you do the kind of same thing for big LP, you're going to break the fact that we're dealing with a holomorphic function. So what you get is the next best thing. Well, by Holder's inequality, this is still true. This norm here is less than or equal to the AP prime norm G. But all you can do is say that this is less than or equal to the LP norm of this, we call this the Bergman projection, just to give it a name, just because it's the L2 orthogonal projection onto the Bergman space A2. So yeah, call this a Bergman projection. So it's this norm here times the norm of phi for my phi, phi g. Okay, so what's the proof? Well, the proof starting off is literally Hahn-Banach theorem. Pick something in AP star. And let phi tilde be a Hahn-Banach extension to LP. So here, this is obviously, maybe I should do blue. This is my M for invoking the Hahn-Banach theorem. Well, since phi is an LP, so I mentioned LP duality works, well, certainly I did say for any subset of Rn, n equals 2. Disk is a subset of R2. So there exists G. Well, it's not my G that I want because it's just an LP prime. It's not holomorphic necessarily. I guess it could be in theory, but there's no reason to think it is. So this here is going to be given by phi g tilde of f. Just remind you, that's just integration. Sorry, there is no g yet, so g tilde. For f in LP of the disk. Okay, so I claim that my original bounded linear functional is given by phi g, where g is this perfectly nice holomorphic function defined as you take the Bergman projection, apply it to G tilde. Why is this true? Well, let's see. Really, this is just a consequence of Fubini's theorem. So if F is an AP disk, then the Hahn-Banach extension, well, it's an extension of phi on AP. So this is given by, well, so I don't want to do that quite yet. So F is an AP, and I mentioned that one of the properties of this Bergman projection is that it is the identity on AP. So this is equal to PF. What is this? Just write everything out. PF is going to be F of W 1 minus Z W bar squared dA of W. Well, phi tilde is given by phi G tilde. So this is going to be G tilde of Z bar dA of Z. So now I just use Fubini's theorem, and I'm justified in using Fubini's theorem by just smashing in absolute values and using Holder's inequality in conjunction with the fact that this is bounded on LP. Okay? This operator here is bounded on LP. So you can use Fubini's theorem. No issues about justifying Fubini's theorem whatsoever. Okay? So I'm going to do the Z integration first and see what I get. Well, I can pull out the f of w. You should probably kind of know what you're going to get. We know that an orthogonal projection is self-adjoint. And this is kind of like maybe do this above here. This really is basically like PF inner product G tilde, because the inner product is integration. So you would expect that, well, you would think it's reasonable to think that I can just move the P over, and that's literally what Fubini's theorem says. It's just when we're dealing with a Hilbert space, you don't have to use Fubini's theorem because it's just it's an orthogonal projection. Right, so Fubini's theorem says this is going to be with a bar here, 1 minus, well, we take the complex conjugate of this here, it's WZ bar. Move this up a bit. And this here is exactly going to be by definition, this whole thing here, without the complex conjugate, is going to be P G tilde of W. So this here is, by definition, this linear functional, bounded linear functional, phi PG tilde of F. Okay. Right. So what we've proven is phi is given by phi P G tilde. Okay. And we crucially needed F as an AP so that, you know, this Bergman projection PF, or Bergman projection applied to F, gives us just F back. Right. For G and P, G tilde. I mentioned that actually, for if G tilde is an LP, this is going to be an AP. In particular, it's holomorphic, P applied to G tilde.